Welcome to part 2 of utility functions. In this presentation, we're going to discuss how to elicit utility values from a decision maker. We will also discuss the axioms of utility theory. So we saw in previous examples how you can take a person's preference on certain outcomes and quantify that, and then apply it to a decision tree to get a result. But how do you actually get those values? How do you know that the person prefers X over Y? You gotta figure that out from a person somehow, right? So how do you actually calculate a person's utility function? What does it actually look like? Um, to keep it very simple, we're going to use a very simple technique here. We're going to use a series of hypothetical lotteries to reveal a person's preference. So I'll jump right to an example here. Which of the following do you prefer? Do you prefer option A, which is a $30,000 guarantee, or option B, a lottery ticket which gives you a 70% chance of $60,000 and a 30% chance of losing $10,000? If the decision maker's response is 30% chance of losing 10,000 is just too risky for me, I'll take the 100% certainty here and take the 30,000, that act reveals something about that person's preference and their attitude about risk. Let's continue our conversation with the decision maker. So, as a follow-up question to the initial offer of $30,000 guaranteed, or a lottery ticket that gives you 70% chance of 60,000 and 30% chance of losing 10,000, we're going to give the decision maker another offer. Let's change the offer here. Which of the following do you prefer? Again, we'll offer a $30,000 guarantee, or option B, this time a lottery ticket, which gives you now a higher probability, so going from 70 to 90% chance of winning 60,000 and a 10% chance of negative 10,000 or losing 10,000. Now let's say the decision maker responds, I will get the lottery ticket in this situation. Okay, so the probability of winning 60,000 has gone up from 70% to 90%. So based on the decision maker's response, they switch from the guaranteed 30,000 to getting a lottery ticket. So what does this reveal? Okay, this reveals that the point of indifference between certain money and the lottery ticket, it lies somewhere between 70% and 90% chance of winning $60,000. So we know this decision maker, their indifference point lies somewhere between 70 and 90% chance. Okay, so somewhere in there, we know they'll be willing to trade off a $30,000 guarantee with a lottery ticket for $60,000. We're going to continue our discussion with the decision maker. Based on the first two options, we know the decision maker is indifferent of winning $30,000 or a chance of winning at $60,000, given that the odds are somewhere between 70 and 90%. So we know based on our previous, between 70 and 90%, the decision maker is indifferent. Okay, so we're going to offer another option here. Okay, so we're going to change the offer one more time. We're still going to offer the $30,000 for certain, but now we're going to change the probability to somewhere between the 70 and 90%. So we're going to pick 85% here. Okay, somewhere between 70 and 90%. Okay, so a lottery ticket that gives you an 85% chance of winning 60,000 and a 15% chance of losing 10,000. Okay, and for this offer, your decision maker says, oh, I am now indifferent between the certain money and the lottery ticket. So they could take either option A or option B in this situation. So now the decision maker has revealed something that we can use here to build the utility function. Okay, so the utility of this $30,000 guarantee here, we actually know what this is now. Okay, so using that 30,000, okay, we can now calculate the utility of 30,000 for this decision maker. The utility as a function of dollar amount. So $30,000 in this case is a combination of an 85% chance of winning $60,000 and a 15% chance of losing 10,000. Okay, so this is a 1 and a 0, right? Okay, we know that's the maximum that you can get here is 60,000, and the worst that could happen is losing 10,000. So utility value, the maximum amount is 1 for the $60,000 outcome, and negative 10,000 is losing 10,000. That's my worst outcome. That's our worst outcome here. So it's a 0. Okay, so we evaluate that, and then we get a utility value of 0.85. Okay, so this means for this decision maker, $30,000 is equivalent to 0.85 in terms of their utility value. Okay. We will repeat these for the other amounts to get the utility for each of the other amounts respectively. So our example previously shows you a way to elicit the utility of a decision maker. We try to get the true nature of a person's preference. And you could probably tell from the process that this could be somewhat problematic and it could be cumbersome. Okay. Utility assessment based on the probability equivalency approach can be difficult. And I think the biggest risk to this process is after you go through this process, is it truly reflective of the decision maker's preferences? Does it do a good job of actually revealing their true preferences or not? And different studies have shown that it may not. And one big flaw to this whole process is that many decision makers, any human being basically, we have a very tough time distinguishing between 90% or 95%, for example, or 10 to 15%, etc. It's really difficult for us to make that judgment. So what are some ways to overcome this issue? Ultimately, we want a process that truly captures a person's preference appropriately, so that we can be as reflective of that person's preference as much as possible. So a different approach is simply use 50-50 lotteries or 50-50 gambles. Don't use any other probabilities, but just 50-50. Okay, so here's an example. We want to elicit a decision maker's utility function for values from 0 to $40,000. So the assumption here is then the utility for $0 is 0, and the utility for 40,000 is 1, the maximum utility. The question we would ask the decision maker is, how much would you be willing to pay for a lottery ticket which gives you a 50% chance of winning 40,000 or 0 otherwise? And let's say the person says $10,000. Okay, so the implication here then is because based on what we have, we could actually figure out what the utility of that $10,000 is. Okay, so the utility of 10,000 is simply, because we're using a 50-50 lottery here, 50% times the utility for $0, in our case is $0, plus 50% times the utility of $40,000, which is $1 here. Okay, so the utility for 10,000 then for this decision maker ends up being 0.5. Okay, so this is, by using a 50-50 lottery, we've now figured out, or we deduced the utility for this decision maker for the value of $10,000. So we're going to continue here with this 50-50 lottery process. So based on our previous response, we know the utility for this decision maker at $40,000 is 1, at $10,000 is 0.5, at 0 it's $0. We can now figure out the utility for values in between these. So for example, we can basically figure out what are some values between $40,000 and $10,000, right? There's got to be some utility value between 0.5 and 1, but based on what the responses are, it'll tell us what the shape of this utility curve is going to look like. After we figure that out, we can actually figure out then the values between 0.5 by looking at lotteries between 0 and 10,000. Okay, so give you an example. Let's start with the values between $10,000 and $40,000. Question: how much would you be willing to pay for a lottery ticket which gives you a 50% chance of winning $40,000 and a 50% chance of $10,000? So again, we're sticking with this 50-50 lotteries instead of using other probabilities to make it easier for the decision maker. Let's say the decision maker says $18,000. Okay, so then we actually can now calculate what the utility value is for $18,000 for this decision maker. So again, we're going to set up the equation. The utility for $18,000 is 50% times the utility for 10,000, which you figured out previously, which is 0.5, plus 0.5 times the utility for 40,000, which is still 1. So then the utility for $18,000 is 0.75 for this decision maker. Now you can kind of tell now we can pick values between, now we can $18,000 and $40,000 if you want to keep going to get values in between, 0.75 and a 1. We could keep going. Let's go on the other side of this though, between 0 and 0.5. So another question, right? How much would you be willing to pay for a lottery ticket, which gives you a 50% chance of winning 10,000, 0 otherwise? Okay. So this time we're trying to figure out the values between these 2 points, right? Okay. So let's say the answer here is $3,000. Then, based on this response, we now have the utility value for $3,000 for this decision maker. The implication is the value for $3,000, utility value for $3,000 is 0.5 times the utility value for the 10,000, which is 0.5 for this decision maker, plus 0.5 times the utility value for $0, which is 0 for this decision maker. So the utility value for $3,000 for this decision maker is now 0.25. And we could keep going, right? And we can figure out values between, for example, 3,000 and 10,000 again, from 0 to 3,000, right? There's intermediate points. We can keep going if we wanted to. We can look at the results from our lotteries here. So based on these 50-50 lotteries, this is what we know about this decision maker. Now again, you can figure out intermediate points if we wanted to, right? So we can now go between these two values to figure out the utility values and the monetary amounts between those two, and then between these two, and these two. And you can even go even more detail within that, right? So, this is a very kind of a iterative, consistent process to this. Ultimately, though, I think the biggest question for me and probably for you as well is, do these utility elicitation process work? Does this approach actually work? Okay. So the answer to this, it really depends on how well the person getting the utilities from a decision maker, how well they do this process. Okay, so evidence suggests that the utilities appear to be extremely sensitive to the elicitation process. So you have to assume the preference of an individual does not change, right? Whether someone preferring a $10,000 guarantee versus a lottery ticket that offers X percentage of winning and Y percentage of losing for $50,000, $80,000. Their preference is their preference, right? That's the assumption. Okay, but depending on how you present these lotteries or how you question the decision maker, it may have you may get a very significant difference in terms of the outcomes. Okay, so you have to be very careful in how you craft these questions and how you generate these utility functions, because it is very sensitive to this utilization process. There are flaws and inconsistencies in the utility values. The Allais paradox, which is referenced in your additional optional reading, you can take a look at that as well. Human beings are complex, right? We're always inconsistent and we're always flawed, right? So I think this is reflective of that as well. But in decision theory, you want to get the as close as possible. You want to reflect a person's preference as close as possible. So we have to be really mindful and be very cautious in how we approach in this utility elicitation process, so that it could be as reflective as possible. So in the previous part of this presentation, we've explored how to actually elicit the utility values from a decision maker. We've also explained how, although this process is imperfect, There are a lot of flaws, but this is the de facto way of eliciting the utility values, and it is still very effective in terms of doing the analysis, etc. I'm going to quickly kind of discuss some of the axioms of utility theory. What are some of the underlying assumptions when we're doing this type of analysis to kind of help us understand like what's appropriate, what's inappropriate, right? So again, these are like the axioms. So when we're doing these utility value calculations, these are kind of stipulated already, right? So axiom one is orderability. So the brief explanation of this is decision maker can compare and make consistent choices between alternatives. Faced with alternatives A and B, they will always prefer one to the other or be indifferent between them. So, they're going to be a decision maker understands and knows how to order different processes and is consistent, right? So again, this might be somewhat problematic in a real world setting because again, the way people rank their preferences may change on how that's elicited, right? So, but the underlying assumption we're using the utility theory and utility values is that the decision maker is able to compare and they're consistent with their choices. If they prefer A to B, they will always prefer A to B. If they're indifferent between A and B, they will always be indifferent between A and B. The second is um, the transitive axiom, and this stipulates that if a decision maker prefers A to B and B to C, then they will prefer A to C. So this is a standard transitive property that many of us probably saw in different math classes in our lives. So this also holds in utility theory. And there are a few other ones here: axiom 3, axiom 4, axiom 5, axiom 6. I'll show an example for each one of these so you understand the underlying assumption of utility theory. So we'll move on to axiom 3 first. Let's discuss axiom 3, substitutability. If two choices are indifferent to the decision maker, then they can be substituted for each other. I'll demonstrate with an example. Okay. So for example, if the decision maker is indifferent between these two lotteries, lottery 1 is a guarantee for $15,000 and lottery 2 with an 85% chance for $30,000 and a 15% chance of losing $10,000. If the decision maker is indifferent between lottery 1 and 2, then the following could also be claimed as well. Okay, so the decision maker will also be indifferent between lottery 3 and 4. I'm going to point out where this is coming from. Okay, so this $15,000 here, okay, you can substitute that $15,000 with lottery 2. Okay, so lottery 2 is substituting $15,000. Why? Because we know the decision maker is indifferent between a guaranteed $15,000 and this lottery for lottery 2. Okay, so we can directly substitute that $15,000 with lottery 2, and that's where this part of the tree is coming from. Okay, so that's directly lottery 2 right there. Right, so this axiom 3 substitutability allows you to make this substitution. Axiom 4, monotonicity. This axiom claims if two options have the same two possible outcomes C and D, and the decision maker prefers C over D, they will also prefer the option with the highest probability of C occurring. Okay. This could be very easily seen with an example. So let's look at, we have these two lotteries, lottery 1, okay, and lottery 2. Lottery 1 has one outcome for $60,000 and the other outcome losing $10,000. And it's got a 75% probability of winning $60,000 and 25% chance of losing $10,000. Lottery 2, on the other hand, has the same outcomes, winning $60,000 or losing $10,000, but the probabilities are different. Okay, so the assumption here is for most decision makers, I'm assuming here, is going to want $60,000 over losing $10,000, right? So this is basically outcome C here and outcome D, according to our example. Okay, so assuming that the decision maker prefers outcome C over D, then they will also want the highest probability of C occurring. So what that implies is the decision maker will prefer lottery 1 over lottery 2. Okay, so these are my probabilities, right? This is my P, this is the 1 minus P. Okay, now if we prefer the C outcome, we're always going to want the lottery with the higher probability of C occurring. Okay, that's what this axiom is assuming. Okay, decision maker will prefer lottery 1 or lottery 2 in the following example. Axiom 5, decomposability. A decision maker will be indifferent between a compound lottery and a simple lottery, which offers the same rewards with the same probabilities. So I'll show you this with an example. Decision maker will be indifferent between lottery 1 and lottery 2. So let's look at lottery 1, lottery 2. So where is this coming from? So according to this axiom decomposability, the decision maker should be indifferent between lottery and lottery 2. Okay, so let's see where these values are coming from. So if you look at lottery 1, and if you follow this top branch here, okay, you have 0.4 times 0.7, which is 0.28. Okay, that probability will yield a net result of $60,000, right? So that's where this 0.28 value is coming from, that probability. Okay, now let's look at the negative 10,000. So you notice here, right? Both of those have the same outcome, negative 10,000. So in this case, we're going to take these two values, 0.4, 0.3. Okay, we're going to take that value, which is 0.12. Okay, now we could just add this value to 0.6 to get 0.72. Okay, and that's where this value is coming from. Okay, it's got a net outcome of negative, losing $10,000, right? Okay, so according to this axiom, the decision maker will be indifferent between these two lotteries because of decomposability. And finally, axiom 6, continuity. We've actually already applied this quite a bit. If the decision maker prefers A to B and B to C, then there is a probability P for which they are indifferent between B and an option that yields A with probability P and C with probability 1 minus P. So we've already applied this a few times. For example, there exists some P where the decision maker is indifferent between lottery 1 and lottery 2. I'll show you lottery 1, lottery 2. So in this case, this is kind of like, we've seen this example in multiple cases, but when we're eliciting utilities, we actually use this in the past examples. So the assumption here is A is my best outcome, okay, and my C is my worst outcome here amongst these three, and then B is somewhere between, right? Okay, so for a guaranteed B, there's some probability P for getting A and some probability then 1 minus P of getting C, where these two lotteries are now equivalent, right? Or indifferent between lottery and lottery 2, right? So again, the assumption here is that A is the best, then B, then C, okay? If we have these rank, okay, there's some probability P of getting the best outcome A, and some probability 1 minus P then of getting the worst outcome C, then now you're indifferent with getting 100% guarantee of outcome B. This marks the end of the presentation. Thank you for watching.